Hi, everybody. The clock has striken 2 from where I can see it. So I say let's start the webinar now. And people can, of course, join underway. That's completely all right. So hi, everybody. It is my pleasure today to welcome you all to today's webinar. The focus today will be on techno-economic analysis of a biorefinery. The webinar will be delivered by our talented guest speaker, Humzaa Imtiaz Ullah. So Humzaa, special welcome to you and thank you for taking out the time today to deliver this webinar, and thank you to all in the audience. Thank you for joining us today. We look forward to seeing what Humzaa has to share with us today and looking forward to getting smarter on the techno-economic analysis area. So onto the agenda. As the agenda can be seen on all your screens, we are starting with a small welcome, followed by a small introduction to the organization, Chemical Engineering Life. This is followed by a case study and a workshop based on the topic of techno-economic analysis. There will be a small question and answer session at the end to clear any doubts that might arise along the way. So make sure to hold off to your questions till the end and we will look into them. So as I said earlier, our guest speaker today is Humzaa Imtiaz Ullah. Humzaa graduated as a chemical engineer from the Technical University of Denmark, where he obtained the degree of Masters of Science in Chemical and Biochemical Engineering. His talent within the field of techno-economic analysis is evident by the fact that he's published 2 scientific papers, which were both based on techno-economic analysis and sustainability. Therefore, I think we're definitely in for a treat today. He is thriving in the field of engineering, but he also holds a vast amount of experience from other sectors, such as the corporate world, with a special focus in procurement and IT. At the moment, Humzaa is working as a quality management systems engineer within the pharmaceutical sector. Now, a small introduction to the organization, Chemical Engineering Life. As you all can see on your screens, our goal is to connect chemical engineers from around the globe, just like today, where we have an audience of people from all around the globe. Now you might ask, how is it that we actually connect the engineers from around the globe? Good question. There are multiple initiatives that we have taken to do so. One of our initiatives is creating a community of engineers so that they may connect and network with each other. This can be, you can become a part of the community by becoming a free member on our website. We also share interviews of chemical engineers from around the globe where they dive into and tell us what they do and how they do it. And this acts as an inspiration for the readers and shows how many different fields within the field of chemical engineering exist. We also run a mentorship program. This is a biannual program where we connect young professionals to more experienced engineers from around the globe. And like we are doing today, we host webinars. Our webinars are done on different topics, and these are done by people who have a lot of experience within the topic that they showcase to us in our webinars. And all the people who are host the webinars are the one who, let's say, they know what they're talking about. So it's no joke. So make sure to become a member on our website. And to become a member, it is completely free. So honestly, why not do it? By becoming a member, you get head start invitations to all our different initiatives. So you don't miss out on anything, whether that is our webinars, the mentorship program, the interviews, everything. And so that is it for what we do at Chemical Engineering Life. Now I will pass on the mic to Humzaa Imtiaz Ullah because I'm sure you are all very eager to learn about the economic technical analysis. So let's do it. Welcome, Humzaa. The mic's all yours.
Great. Thank you so very much, Emma. Thank you for the great introduction. And hello, good morning, good evening, everyone. Thank you for joining us today for the webinar and for willing to listen to me speak about techno-economic analysis. So to begin with, let's talk about what exactly is techno-economic analysis. And techno-economic analysis is defined as a method of analyzing whether about the economic performance of an industrial process. Basically, just asking yourself the process that you are designing as a chemical engineer, will it or will it not make any money? And that is much more important than many people perceive it to be, because in reality, every process or every project that you work in as a chemical engineer or as any engineer, at the end of the day, it all comes down to dollars and pennies. If the process that you have designed, if it is not making or generating any profit, then that project will never see the end of will never be implemented or actually go into production. So therefore, when you are designing a process, you need to be able to keep in mind that the process that you are designing always is profitable, is capable of making money, and the money that you will generate from your production can be used to further expand or to sustain your own expenses within the production. And that is something that we'll do today. The general process of doing techno-economic analysis is that you start off with your process data. The very first step is that for all the design that you have created, that you have made, you need to find the equipment cost. The equipment cost is something we call the total installed cost. That means that for example, when you have a heat exchanger, it costs a certain amount. Then you also need to calculate how much will it cost when it is installed in your production site. And that is what we call the total installed cost. You do that for all of your equipments. You find the sum of all of them. Using your equipment cost, we can then go in and find our capital investment. The capital investment is the money that you need in hand to basically build your plant, or the money that you need to start your business. By doing so, then the second step then is that you need to perform your mass balance and energy balance. Through the mass balance, we then find our raw material requirements, product production, the waste production, and then of course you need to buy your raw materials, you need to sell your products, and you need to pay for your waste that is being produced. Using the energy balance, we can then calculate our utilities cost, and the utilities, they include everything from steam, cooling water, electricity, refrigerant, and anything else that you might need for running of your plant. And once you have done that, and you have your capital investment, and you have your day-to-day operation costs, we can then go ahead and calculate something we call a total annual product cost, or is also referred to as PPC. This is the amount of money, the minimum amount of money that you need to run your plant annually. So that means that if we calculate that you need $10 million per year, that means that you need to have $10 million in hand by profits or by investment or by any other means to make sure that your plant keeps running. Once we have this value, then using all the other variables, we can then move on and calculate our economic metrics. There are multiple metrics that we can use to calculate the profitability of a plant. But for the purpose of this webinar, we're actually going to focus on return on investment, payback period, net present value, and the minimum selling price. And we'll dig a little deeper into what exactly they are and what they mean. Once you have the metrics in place, and this part is very important because everything that you do up until this point, it all is very theoretical. We are not actually building a plant. We are not, you're not going to be calling actual suppliers and asking them the cost or the realistic cost of each and every equipment. But all of this is done through literature study. So when you're doing mass balances or energy balances, the price of your raw materials, your products, the cost of how much electricity costs, these all will have to be taken from literature. And therefore, it is very important for you to understand that all of all the calculations that you do, you need to be able to verify and validate those numbers. One way of doing that is, of course, you can do sensitivity analysis. Now, the sensitivity analysis does not really cover the validation or the verification part, but it covers the uncertainty that you might have in any of these numbers. One example is, for example, if I was looking at a raw material cost, let's say I'm buying methanol. If you were to take the price of today, but the price of methanol is dependent on the market, so it can either go up or it can either go down. Tomorrow, it can increase by 10%, it can increase by 20%, it can also decrease by almost 50%. That is something that is entirely dependent on the market. These sort of deviations, that is something we cover through sensitivity analysis. And again, this is something that we'll dig deeper into this webinar today. And finally, you can also do uncertainty analysis. We have decided not to cover the uncertainty analysis in this webinar, but the uncertainty analysis covers how certain or uncertain your values that you have used are using different probabilities functions, something we call a Monte Carlo analysis. So coming up to the economic metrics, and it is very important that we understand what these metrics actually mean and what it is that they are covering. So firstly, the metric that we have decided to look at is the payback period. So when you get an investment for your project or for your production, the payback period tells you how long will it take for you to fully cover those expenses. Let's say you're buying a shop and you go to the bank and the bank gives you $100. Then you need the payback period tells us how much time will it take for us to pay back that loan 100% to the bank. And that is calculated as, so you have your total investment divided by your average annual cash flow. So how much money you make in a year for your investment divided by your annual cash flow per annum. And that's you end up getting the years, how long will it take for you to give back the money. The shorter it is, the better. The longer it is, the worse it is. Because if it takes you 20 years to pay back your capital investment, that means that you're not making that much money to cover up your expenses and your investment. And your investor might ask you that if they're gonna see all the money in 20 years, then they are better off investing in someone that will be able to pay them back in 1 year. The second metric that we decided to look at is the return on investment. And it tells you it is a fraction of total capital investment covered each year during the investment period or the total project time. So let's say we have a production for 20 years and you need to be able to understand, or you need to be able to tell your investor about how much money did you actually end up making with respect to your investment. And of course, it should always be more than one, like more than 100%. So you have and the way we calculate it is your annual profit divided by total investment. And this part is very important. As you can see, it is your profit that you need to calculate and not your annual cash flow. So let's say I'm selling something for, let's say I have a shop and I'm selling something, my annual income is $100, right? But that $100 is not my profit. I need to pay taxes, I need to pay salaries, I need to pay my expenses. And let's say my profit comes down to $20, right? That $20 then divided by your total investment. And let's say the person invested $10 in my shop, when my profit is $20, so that will be 20 over 10. That means that my profit is still, my ROI is still 100, double what my investment was. And this is very important because many people, they end up using the actual cash flow. It's not, it is your annual profit that you're going to be using. Finally, we have is the net present value. The net present value, it relates how much money your investment will be worth in coming years. So let's say you have 20 years. It calculates how long. It calculates the time value of your investment. And the time value, in order to understand, is that you all have to understand that with time, the value of money changes. The money that you have today is going to be worth a lot more than the money that you're going to have in a year from today. And the reason is that today you can buy, let's say you have $10 today, you can buy more stuff with it because it has more buying power. But in 1 year time, due to inflation, due to some other variables, due to the market fluctuations, if you're going to have $10 in 1 year time, that's not going to be as powerful as the $10 you had today. So with time, you actually end up losing value unless you invested your money in a bank, or you took interest on it, or you made a business with the money that you had today. And the NPV, the net present value, is something that calculates how worth your money will be in the coming years. And the way we calculate it is the N, it is the number of years. So the N year of total cash flow, so you sum up all the money that you have earned so far, you divide it by something we call a net present worth factor. And it is calculated as 1 plus discount rate to the power of n, where n is again the number of years. The discount rate is the rate that is given to you depending on how risky your investment is. Now you must like the less risk there is, the lower the value will be. The more the risk there is, the higher the value will be. Now, for the purpose of this webinar, as I'll tell you later on, we have decided to use the discount rate of 11%. And now you're going to be wondering that what makes something less risky and more risky in a chemical process environment. And the easiest way to do it is that if something is developed, if something has a very good market, if it is something that has been done before you, it's going to be very low risk for the bank, for your investors. So let's say if you want to go and build a plant to produce methanol, that's very low risk investment. Why? Because it has a great deal of market. It has a great deal of examples. Many other companies have done it before you, and they all have been quite successful at it. So the investors are going to be able to do it. But let's say you go in and you tell someone that you want to produce biodiesel, for example. Now, the biodiesel does not enjoy that huge of a market as methanol does. Biodiesel is not something that is readily available. There are not a lot of companies out there that are working with it. So now the discount rate would actually be slightly higher. And like I said, since we're going to be looking at biodiesel production for this webinar, I have selected the value of 11%. And these values, you pick them from literature. There are different factors that you can use to calculate. There are different, like for example, if you were to look at different intervals, the lower the risk it is, it takes a value between 0 and 1 to 5. If it is medium risk, you can pick a value between 6 to 12. If it is very high risk, then it can go up to 15%. So great. Then that would be the brief. That was all for a brief introduction about techno-economic analysis. Now we'll dig deeper into the applying techno-economic analysis to a case study. And now for the purpose of this webinar, I have decided to work on biodiesel production. And the data or the methodology that is being presented here is slightly inspired from my own research paper titled An Integrated Biorefinery that has been shared with all of you before the webinar. I hope you all had a chance to look through it. But if not, we're going to go through key values in the webinar as well. So the general process for the biodiesel production is that we're going to be using waste cooking oil and methanol. We use that in a catalyst process, and then we create biodiesel and glycerol. Now we are using waste cooking oil and methanol, and the waste cooking oil is actually a waste product. So already there, the idea behind using the waste cooking oil is that it is cheap. It's easy to find. It's cheap. It's a waste stream. It's not a valuable product, so it can be acquired at a very low price. Methanol, well, that's one of the processes that is the requirement of the process. And then we produce biodiesel and glycerol. And now the purpose of biodiesel production, of course, is that we are moving towards, we are facing many climate challenges around us. And instead of using petroleum fuel, biodiesel can act as a very good alternative to petroleum fuel. So in that way, you can see that the process that we're using for the production of biodiesel can be in high demand. It is very useful. It is a major requirement for our global, for fighting up the challenges of climate change. And therefore, it can be argued that it is not a very high risk investment, but it is at a somewhat medium level investment, because even though it does not have a strong market right now, but as we're going into the future, it might create a bigger market. So therefore we have, like I said earlier, that we have used a discount rate of 11%. So the very first thing that we need to look at, that is the equipment and the capital cost. The equipment cost can be calculated using the formula that is shown on the slide. Now, there's one thing. Now, I don't want you all to confuse. These are two different terms. So when you say equipment cost, that is the cost of your equipment. But then we have something called installed cost, and that is the cost of your equipment that is installed into your facility. So let's say I want to buy a flash tank, and a flash tank costs, let's say, $20. That is the equipment cost. What we want to calculate is the total installed cost. And that means that we need to calculate the cost when that flash tank is also installed within our facility. So the first thing that you need to do is that you have your requirements. So you design your equipment, you calculate the capacity. The capacity is not the correct word, but it's actually the variable that you're going to use. For example, when you're working with a flash tank, you use your cubic metrics with the volume. When you're using the heat exchanger, you use area. So therefore, for a flash tank, it would be your volumetric capacity. So let's say you need 50 cubic meters of capacity for your flash tank. Then what you do is you go in and you scout to literature, and you find the cost of for a given you find the cost for a given capacity within a book or within a literature study. So that means that you find a paper, and many of the times it's good to always use validated papers, papers that have been written by maybe the government or different universities. And let's say you find from a paper that 10 cubic meters capacity of a flash tank costs $5. That's an example. Then you put that into that formula, and the N value that is also the scaling factor, and that is to be found from literature as well. It is different for each equipment, so you can't just use the same value for all of them, but it's different from flash tank to distillation columns to heat exchangers and so on. By using that first equation, then what you're doing is that you are finding the cost from the base cost to the capacity that you need for your equipment. And that is something we call the scaling law. Once you have that price, so that means that for your 50 cubic meter flash tank, it's going to cost you, let's say, this amount of money. Then that is not necessarily for the year that you're working in right now. So let's say we are doing an analysis in 2022, and the price that you found was from 2005. It is always best to find the prices within the last 10 years, because then they are the newest prices. It's not a good idea to go back and find a price from 1940 and then convert that to now, because that's a great deal of error and uncertainty. So it's always a good idea to use the prices within the last 10 years. And the way then of course you need to convert it to your present year. The way you do it is that we use this number called a CEPCI, which stands for Chemical Engineering Plant Cost Index. Every year has a special value. So you find the value. So let's say we found the price from 2005, and you take the value from 2005, and you find the value for the year that you were doing the analysis for, and then you convert that year's price to your current year. So now what we have done so far is that we found the price for our capacity, then we converted that price to your current year, and then finally, like I said in the very beginning, you need to find the cost once the equipment has been installed. Then we multiply those price with our installation factor. The installation factor itself is very different for each equipment, and that can also be found from literature. For the purpose of this webinar, I have selected my equipment cost to be $10 million. Once you have your equipment cost and you have your total installed cost, you can then go on and calculate your total capital investment. The total capital investment is the sum of your fixed capital investment, FCI, and your working capital. And the fixed capital investment is the investment that you need to basically build your plant. That is all the money that you need to build a proper functioning facility. Everything from equipment to your piping, to your instrumentation, your legal fees, everything, all that you need to prepare to create a physical asset or to create a physical building, that comes under fixed capital investment. To make things slightly easier, the fixed capital investment has been divided into divided into subcategories for your direct cost and indirect cost. The direct cost is something that you need, that is the money that goes directly in your production facility. Direct cost, that means it includes everything from equipment, transportation of equipment, installation of equipment, piping, instrumentation, maintenance, paint, everything that you are doing within your production facility, that money needs to be taken from your direct cost. Then we have something called an indirect cost. The indirect cost is all the money that is required for the production, but it's not actually being used within the physical assets. For example, it could be anything in legal fees. It could be your contractor fees. It could be your, you need security. All the administration duties or administration cost of making sure that your plants get built, that needs to be covered by your indirect cost. And your direct cost is something that covers the literal building of your facility. Now, your direct cost should, of course, always be higher than your indirect cost. And I'll get into it in a minute on why it is. The way we calculate the direct cost and the indirect cost is that we use our total installed cost of our equipment as a base value. And you multiply a factor with that equipment cost. That should give you your direct cost, and that should give you your indirect cost. For the purpose of this webinar, I selected 1.69 as a factor for my direct cost and 1.32 for my indirect cost. What it means is that means that my direct cost is 1.69 of 10 million, and my indirect cost is 1.32 times by 10 million, and that then gives me my cost. But you have to be very careful here because, like I said, for the direct cost covers all the assets. So you need to add your equipment cost, which is my 10 million, plus the factor times by 10 million. So that means that my direct cost is not just 1.69, it's actually 1.69 times by 10 plus 10 million. So you have your equipment cost, you calculate the direct cost, you multiply the factor, that your direct cost is the sum of those two values. Your indirect cost, the indirect cost does not cover equipment. So there you don't have to add your equipment cost into the factor, but you only have to multiply the factor with the equipment cost. And this is something where a lot of people make mistakes, that they forget to actually add the equipment cost within the direct cost, thinking that it's covered, but it's not. It's very important that you add them up together. And then you can see we have done the calculation here. So we calculated the direct cost plus the indirect cost, and that gives us a fixed capital investment of $39.5 million. So that is our fixed capital investment. That means that I'm building up my plant. I got 40 million. I built my entire plant. I have all my equipment. I have all my legal department ready. I have everything I need. I got the keys. Then you come down to the working capital. Now, the working capital is the money that you need in hand to actually kickstart your production. The working capital is also calculated as a fraction of your equipment cost. And as you can see on the screen, I have used 0.8 of the 0.8 as a factor. So 0.8 times by 10 million, that means that our working capital will be 8 million. So what exactly does working capital cover? It covers everything that you need to kickstart your production. So I need to buy my raw materials. I need to buy my utility. I need to pay off my bills. I need to hire people. I need to pay people off for their salaries. I need to pay off the engineers and the operators. And you need to do it for at least 6 months. You need to do it for at least 1 year until you start making profit. That money should be covered by the working capital. The working capital should more or less cover all of your expenses that you need to literally kickstart to your production. And in case you don't make a profit for the first 2, 3, 6 months, that should be then covered by the working capital, because you cannot expect, and this is something get into later on as well, that let's say you build the plant today, you can't expect that from tomorrow you're going to have 100% production. But instead, in the first year, you only have 80% production. In the second year, you have maybe 90%. In the third year, maybe you might have 100%. So therefore, keeping that in mind, you need to use working capital to cover up the cost that might not be covered by your profits. And like I said, it is around 0.8 factor multiplied by the equipment cost. But and just so you'll know, these numbers that I have used, they are all taken from literature that I have found. So you could also always go ahead and find different literature, different values, different sources, and this entire analysis would look a lot different. Like you could have used 0.9 for working capital. There is no fixed numbers. These are something that are taken off from books and from literature. Moving on, then the next step that we need to do is, like I said earlier, we need to create our mass balance. And once you have your mass balance in place, then we are going to have our your prices, your requirement per hour, and then your prices for of each material. So as you can see here, for the process, we need waste cooking oil and methanol as our raw materials, and we are producing biodiesel and glycerol. The mass flow is given in hours, but when you're doing the techno-economic analysis, you need to convert all of this into per year instead, because it makes a lot easier when you're calculating the economic metrics, which I showed you earlier, because the economic metrics are based on annual income, on annual cash flow. Therefore, it's a good idea to convert all of that into years. The way you convert it into years is that over there. So you have the total cost that is calculated by the mass flow, which we have right here. So we have over 45,000 kilograms per hour. You multiply it by your production hours. So let's say how many hours you're going to be running your plant per year. So let's say you say that you're going to be running it for 24 hours for 350 days. For these calculations, I have selected that we're going to be running our plant for 24 hours for 350 days per year. 15 days are then kept aside for maintenance or cleaning or whatnot, but we're only going to be running it for 350 days. Then you do 24 multiplied by 350. That would give you your production hours multiplied by the cost. Now you can see that we have a waste cooking oil. It is 45,000 kilograms per hour. We multiply it by our hours, and then you multiply it by the cost. It is $0.2 per kilo, and you end up getting your dollars per year. And you do that for each and every raw material and for each product. The raw material cost is your expense, right? Because you have to pay that from your own pocket. And your product cost, that is your revenue that you're going to be raising by selling your product. The more expensive your product is, the better it is. And the cheaper your raw material is, the better it is. Like you can see already here, for example, the waste cooking oil, it costs 0.2. It's very cheap. The reason it's very cheap is because it's a waste stream. It doesn't possess any useful needs in the market right now. It's a waste stream, so you're buying it off very cheaply. Methanol, again, it doesn't cost that much, around $0.3 per kilo. And of course, biodiesel, it has a very strong market. Even today, it is very expensive. It is $0.9 per kilo. And then we have glycerol, and the glycerol is $0.8 per kilo. The way we find these prices for each of these material, it is not simply enough that you find the cost of biodiesel on the 8th of May, 2022, and you select that value, because these values are entirely dependent on the market. Therefore, the best way to do it is that you find the prices of your product for the past 1 year, or for the past 6 months. If the longer back you can go, the better it is. So you pick so let's say if you go back 1 year for 2021. So you select the period between 1st of January 2021 up until 31st of December 2021. Then you find your maximum price of biodiesel, and you find your minimum price for your biodiesel, and then you find the middle line. for the top plus min divided by 2, and then you can use that price as your cost for the techno-economic analysis. And we have done that, and I've done that for all of them. The waste cooking oil, sometimes it's not very easy to find the prices for some of these materials, like waste cooking oil. You can't really go in and find the price of waste cooking oil on how much it costed a year ago or how much it costs now. Therefore, you can always use a price that you find from the source. And of course, if you're using a price from, let's say, 2015, then you need to account for that you convert that price using the inflation factor to the year that you are doing the techno-economic analysis. So, for example, if the waste cooking oil costed 0.2 in 2018, and you're doing the analysis now, then it's a good idea to multiply it by the inflation factor. And the inflation factor is, you can just find that to Google. And then you just multiply the inflation factor with your price. The next phase, the next step, then that is the utilities cost. And the utilities are very important because the utilities is what is gonna keep the plant running. The main utilities that we have in our plant, that is the high power steam, the low power steam, cooling water, and electricity. And there also tends to be refrigerant if you are cooling something below 0 degrees or so. Luckily, in this case, we don't have any, so I have not added that into the slide. The high power steam and the low power steam, they are two different, they differ in temperature and pressures. So if you want to heat something up to, let's say, 300 degrees Celsius, 400 degrees Celsius, then you have to use high power steam. Anything at a very high level, you need to use high power steam. But if you're heating something up to only, let's say, 50 Celsius or 100 degrees Celsius, then you can enjoy with a low power steam, sorry, low pressure steam. And then of course you have cooling water. The cooling water is again to cool your equipment, streams, and whatnot. And then you have your electricity. Electricity is only mostly used by pumps. And then every production facility does have a requirement for electricity. Like you have your computers, you're going to have your automation system, you're going to have your process control. That also needs electricity, and that is also taken as a percentage of our total capital investment. But majority of the cost for electricity should come from your actual equipment that you're using. Luckily, in this case, we only had a few pumps, so therefore there was not much of a need to actually use electricity. But there was a very high need of using our steam, low power steam, low pressure steam, high pressure steam, and also cooling water. And these prices might change depending on what source you're using. Like I found the source for high pressure steam to be $5.8 per gigajoule and so on. And when you are finding the prices, it is very important that you keep an eye for on the units that you're working with. For example, you can see here for electricity, typically we use watts, but since I found the price in gigajoules, so I converted that into gigajoules. And then once you have your requirement, so for example, for high pressure steam, our requirement is 0.8 million gigajoules per year. You multiply that with your unit price, and you find the total cost per year. And again, just like our raw material and product cost, it's a good idea to do it per annum. So you do it per year instead of just doing it per hour or so. It just makes your life a lot easier afterwards. And then you calculate the sum of all of the cost, and that was to be $5.4 million per year. That means that for me to be able to pay for my utilities, it's going to cost me $5.4 million per year. After the utilities, then we come on to our waste cost. The waste, contrary to what many people might believe, you're not allowed to simply throw your waste into the rivers. That you're not allowed. That's not allowed by any law. So you need to pay for your waste, and the waste has to be classified into toxic waste, non-toxic waste, water disposal, water treatment if you're doing it any, and carbon dioxide emission. Toxic waste is everything that is considered to be toxic. For example, carbon monoxide, that is a toxic waste. non-toxic waste could be something that's not considered not toxic. I believe ammonia is not considered to be non-toxic waste. So if you have ammonia waste, that you will only have to pay the price that is required for non-toxic. But if you have carbon monoxide emission, then that actually comes into toxic waste that you need to pay for. And of course, the toxic waste costs a lot more than non-toxic waste. And that is also to encourage different facilities to reduce their waste production as much as possible. And then, of course, we have our water disposal. Every water that you use, all the water that you're using in your production for cooling, for cleaning, or for all the uses, again, you have to get rid of it. And that also costs money. The money can be in terms of transportation cost. You need to take it away. You need to give it to someone else. That needs to be covered. It is always a good idea to explore the possibility that you can treat the water instead of just disposing it off. Because if the water is clean and you're only using it for example, if you have a fermentation reactor and you're only using water as to dilute within the reactor, then you can always treat it and reuse it back into the process. It does seem that the water treatment might cost you more in terms of just disposing it off, but in the long run, you actually save a lot more money, and your sustainability metrics are going to look a lot better if you're reusing that stream of water back into your process. And finally, we have this something called a carbon CO2 tax. They have it in some countries, they don't have it in some other countries. So if you're doing your production in the US or for example in Texas, Americans, they have a carbon dioxide tax. That means that if you are releasing carbon dioxide into the environment, depending on the emission level, you need to pay a certain amount per kilogram. And that is something that you need to check on. Instead, if you are analyzing your plant that is being produced in let's say Germany, then they have a different carbon dioxide tax. Some countries don't even have a tax. Like I believe if you go in some countries, I believe I checked in Nigeria, they don't implement a CO2 tax, but some countries do, and that is very important that you check it out. If they have it, they need to include it. If they don't have it, then you can get away with it. So now we have covered our investment, we have covered our raw material cost, and now we have our utilities cost, and we have our waste material cost. These are the costs that are important for our day-to-day operations. There are no other major expenses other than these three areas. So using those values, then we can then calculate our total product cost. The total product cost is the amount of money, is your total expenditure per year that you need to run your facility or run your production. It covers everything from raw materials, waste, utility, but also all the other admin expenses that you might have that are important for running a production facility. Like for example, you need R&D expenses, you need marketing, you need distribution, you need to hire people, you need to have tables, you need to have screens, you need to have seminars, you need to have safety additions. All of that needs to be covered by the extra expenses, and that is calculated as earlier when we were calculating the capital investment. We used our equipment cost as a basis for calculating our capital. But when we are calculating the total product cost, then we need to use our fixed capital investment as a basis, and then we find the factors multiplied by the fixed capital investment to calculate all the other variables. So our variable cost, or fixed charges, or general expenses, they're all calculated as a factor of our fixed capital investment. And upon doing so, then you can know how much money you need, and it will always be higher than the sum of all the other expenses that we have talked about so far. So if you can see on the screen right here, so our raw material, it costed around 88 million. Our utilities, it was around 7 million. So if you add them up together, you have around 95 million dollars per year as the sum of utility cost and the raw material cost. But doing all the other calculations, our TPC ended up being $113 million per year. So that means the additional 20 million that came on top of it, that came from all the other expenses that we have talked about here. The variable cost, fixed charges, general expenses, that calculated as a factor of our capital investment. And again, all these charges, all these factors, they are to be taken from literature. I would highly suggest if you are looking up, if you are designing the process, then you use this book called Plant Design and Economics for Chemical Engineers. They have an edition from 2015, I believe, and they have provided with all these other variables and all the factors that you might need in calculating the total product cost. And if not, then if you find any literature, any research paper that have done this Techno-Economic Analysis, they always provide these factors that they have calculated. And of course, these factors, and always remember that these factors, they're always given within a given bracket. So you can't just say, I'm going to pick 500% of my capital investment will be my general expenses. They are always within different ranges that you need to select. So for now, we have our TPC, we have our revenue, but before we go into calculating our economic metrics, we need to take something into consideration. The first thing that we need to take into consideration is how much tax you will be paying for your production. If you are, for example, in Denmark, you need to pay around 25% tax. If you are designing a plant in the US, you need to pay around 30% tax. Again, for example, when we are working with biodiesel, the biodiesel is eligible for a subsidy by the federal government. You can also take that into account. So that means that you will not be paying as much tax as the other production are paying. But the idea is that you need to find the correct tax that you're going to be paying off, because it is the money taken off from your profit. So it's very important that you put in the tax. Inflation, you can take inflation into account. And the way you take into account is that there are two ways of doing it. Either you can take the inflation for your product. So that means that if I am selling my biodiesel today for $0.9 per kilo, due inflation, it's going to get more expensive, right? So next year it's going to be more expensive. The year after it's going to be more expensive, and that's a great thing. That's great. But at the same time, inflation is also going to hit our raw materials cost, our utilities cost, our waste cost. So therefore, we need to remember that when we take inflation into account, it's going to affect all of our materials, all of our expenses equally. And that's the first part of it. The second part is that you could also take inflation, like for example, when we're building our facility, you need to identify how long will it take for you to build your production. So let's say you build your plant in 3 years. In the first year, the cement they had price X. The second year, it got more expensive. The third year, it got more expensive. So you also need to take into account for inflation for that area as well. And so that means that you need to divide it up into two different parts. For the first part is when you're building your facility. And the second part is when we are running the day-to-day operations of our facility. For the purpose of this study, I have taken inflation to be 0. So we assume that we will not be affected by inflation. Everything that costs today will cost the same in 20 years. But if you do want to take inflation into account, but the problem is that it is very difficult to see how inflation will increase in the next coming 5 years, the next 10 years. Something that we saw during this COVID crisis, for example, inflation has skyrocketed because inflation is directly dependent on different international political instability, and so on. So therefore, it can get slightly difficult to find a value that you want to use. One way to do it is that you can look at how inflation has changed in the last 10 years, in the last 15 years, and then you can use the same model the same value for the next 15 years. But again, that is again a huge assumption, assuming that inflation will be the same in the next 15 years as it has been in the last 15 years. But that is one way to do it. But like I said, for the purpose of the economic metrics that I have calculated for this webinar, I have taken inflation to be 0. So I did not take that into account. Then you need to consider how long do you want your project to be. And so typically it's 5 years, 10 years, 15 years, and 20 years. Now the thing is, the shorter project time you select, the less money you'll make. So that's a given. If you select something, a production facility for 5 years, it might prove not to be so profitable because you don't really make that much profit in 5 years. If you were to do something in 10 years, your NPV would be a lot higher. You would end up making a lot more money. If you do something for 20 years, then you end up making a lot more money in that way. But when you are selecting the years, it's not enough that you just say, oh, I'll just select 20 years because I'm going to make more money in 20 years. Because in that way, you can also do a project for 50 years and so on. It's best to select 10 to 15 years because the numbers, like I said, in the case of inflation, it is very difficult to assess how things will look like after 10 years, after 15 years, or after 20 years. So therefore, it's a good idea to maybe always select between 10, 15, 20. Majority of the projects that I have looked upon or worked on, they were between 15 and 20. So not even 10. So it's always 15 or 20 years. And that is an acceptable criteria for Techno-Economic Analysis. Anything more than 20 years, that's more of a stretch. And that's something that is not recommended. Once you have done it, then you need to select and consider about, like I said earlier, you cannot expect that already by tomorrow, you're going to have 100% production in your plant. Instead, you need to identify, okay, so let's say we build my plant this year in 2022. This year, we will only be hitting 50% of our production. Next year, we'll try to hit 80%. And by third year, we'll be able to reach 100%. Or you could also say this year we'll hit our 80%. From next year, we'll start with 100%. And that is why 5-year project time does not make much sense, because if you were to select 80% now and 100% next year, you have already lost 1 year of the profits. So that is something you also need to consider when you are doing the analysis. So for the purpose of this webinar, I have selected the tax to be 30%, inflation to be 0. So we assume that everything that costs today is going to cost the same for the next 20 years. I have selected the production period to be 20 years. And so I select 20. And then I said that in the first year, we're going to have 80% of our production rate. So for the second year, we're going to start producing with 100%. My facility will be built in 3 years. So in the first year, I spend around 25% of my capital. In the second year, I'm going to invest my, again, 30% of my investment. And then in the last year, we're going to invest 50% of our investment. So the facility gets built in 3 years. We're going to have a project for 20 years with no inflation. We're going to pay a tax of 30%, no subsidy. And it is only from the second year that we are going to start with our 100% production. And these are the main considerations. And also, lastly, the discount rate that we talked about earlier when we had to calculate the net present value. I have selected the rate to be 11% because the investment required for biodiesel is neither very low. The risk is not very low because it doesn't really have a very strong market as of right now. Not all of the countries are interested in biodiesel, but it is not a very high risk either because it's not something that we can expect in the coming years due to climate change and environmental challenges, that more and more countries, especially EU and the American government, they are moving towards using biodiesel. So that's why I have selected 11%, which kind of falls right in the middle of in the category of median. So the next step is then to convert all of this data into a calculation part. And I strongly suggest that you do it in Excel. It is very easy to do it in Excel, and it's very easy to keep track of all the calculations when you're doing it in Excel. I have done it in MATLAB as well. I have met a lot of people that tend to do it in Python or in MATLAB, but in my opinion, in my experience, the best way to do it is in Excel. And the way to do it in Excel is that you create one column. You call column A with all of your costs. You could say like what do you call it, like the TPC, your income, profit, tax, and so on. And then you make one column for each year. So you have year 1, year 2, year 3, year 4, up until year 20. And for each year, you calculate how much money you make, how much money is paid off in expenses, which is your TPC, how much money you are going to be paying off in taxes, how much money will be paid off or will be taken in from depreciation. And depreciation is also taken into account when you're doing the Techno-Economic Analysis. And then finally, how much money did you actually end up making from per year? The reason I'm saying per year is because many of the metrics that I'll show you now, they are dependent on annual basis. So if you have the numbers lying around for per year, it just makes it a lot easier for you able to calculate them later on. And then of course you can always sum them up in a cumulative sum or so on. So in that way, it's always best way to do it is in Excel. And I can't stress that enough, that it makes your life a lot easier when you're doing it in Excel. And just a quick suggestion, when you're building up your file in Excel, it is just a good practice of doing it is that you create one tab with all of your variables, all the input variables. That means your raw material balance, raw materials cost, your product raw materials, your cost, utility requirement, the cost, the sum, the variables that we have selected here, inflation, tax, and so on. I have seen a lot of people, they make multiple sheets, and then you need to go into each individual sheet to change a number. And that is just very difficult to manage and very prone to mistakes and errors. Therefore, the best way to do it, and the best way I would suggest you to do it, and the way I do it, is that you go in and you create one sheet with all the numbers, all the variables that you need, and then you make a second sheet with all of your economic analysis or economic modeling. And the economic modeling is, of course, where you make one column for 1 year, for each year, and then in the rows you write your variables. And the variables, they are, like I said earlier, you need to remember. So your income that you're producing, and that depending on how much production rate you have, it is 80%, then you're only going to be selling 80% of your annual product. But so your annual income, then you need to have a row for how much money, how much expenses you have paid. That is your TPC. So then you do your annual income minus TPC. Then you would have one row with how much money you have left. Then you need to pay off taxes. Tax will be taken away from that money as well. Actually, sorry, it's the other way around. So when you have your income, the first thing you do, you pay tax. And then from the taxed amount, then you pay off your expenses. Then the money that you have paid for your expenses, that money is your profit. That is the money that you can then keep in your pocket. If you have investment, then you need to pay off your investment from that money. If you pay off your investment in the first 2 years, then after 2 years, all that money will go straight into your pocket. Once you have done that, then you move down, and then you can calculate the cumulative sum of all of your profit, because the profit is the thing that is going directly in your bank account. So that's the money that you don't need to calculate or subtract any longer. So the more money you add up, and I'll show you in our next slide right here. So this orange line right here, So you can see I have done the exact same approach, the one that I described here. I'm not going to go deeper into the individual formulas because for the purpose of this webinar, the idea is more to have a look at the general methodology and the results. But I will share this slide with you all after the webinar, and then you all can go in and also look at the formulas if you wish. But if you look at this graph here, so we did it for 20 years. Then I calculated the amount of money that I'm generating per year. So you can see for the first year, second year, upon the 20, it took me 3 years to build my plant. So therefore, I have my -2, -1, and 0. And you can see the money is going down because that's where we are using our investments. So that's negative, right? If I'm investing, like you can see right here on the side, our investment was 48 million, and all of that 48 million gets used up in this area. And therefore, the line is going downwards because, you know, it's negative. Right here, you can see this one is slightly below because here in the first year, we only have 80% production. From the second year, that's when we hit it off with 100% production. And therefore, you can see the graph goes down and slightly curve and then becomes a line. It may look like that we are making profit, but please remember, I have not taken inflation into account. So therefore, if I had taken inflation into account, this line, this line, it is actually my annual profit that I am getting in my pocket. So this is around $169 million per year. So that means after paying off all the expenses, my taxes, my TPC, everything, I get $169 million in my pocket. And that is this curve. And you can see it is a straight curve. The reason is because we are not taking inflation into account. So the money, the things that I'm selling today are going to cost the same next month. Therefore, it's the same. On the other hand, this line here, the blue line, it is my cumulative sum. And the cumulative sum is like, and the cumulative sum is basically like if I made 169 million in my first year, 169 in the second year, we add them together. In the third year, I made 169 again, so I add all three of them again. And likewise, you do it for all the years, all the consecutive years, and then you can see the cumulative cash position. It's always going to go up and up and up and up. And yep, and this is a good idea to always plot this graph because already from this graph you can take away a lot of considerations that you have taken into account. So and then once we have done all of that, we can then move on and calculate our economic metrics. The economic metrics, the first metric that we have done, that is the return on investment. It is my profit divided by all of my my investment. It turned out to be 344% per year. That means that my profit, because my profit per year, that was $169 million per year. Let's just say $170 million per year, just for even number, to even it out. My investment was only $50 million. So you can already see right there, compared to that, it is 300%. Our profits were 300% more than my investment. That is what this number means. And this is an average number. So that means annually, per year, for 20 years, my profits were 344% of my capital investment. If you give that number to your investor, they're going to be very happy because that means that the money that they're going to be investing is going to be, they're going to be getting 300% more out of the business. So that's a great thing. And that is something that this should be more than the discount rate. So we selected the discount rate to be 11%. This is 344%. So if it's higher than discount rate, that means that this number or this metric is profitable. The second one that we have is called the net present worth. And the net present worth that I said earlier, it tells us how much, like how the value of money is going to change with each year, like how much we will be worth after 20 years. And that will it's gonna be $1,264 million after 20. That means that after 20 years, we are gonna be worth the time value of the money will be around $1,264 million US dollars, which again itself is a great investment. That means that in 20 years time, the project is not going to depreciate, it's not going to go down in value, but instead we're going to be worth a lot more than what we started off with. And of course we have our payback period. And the payback period, if you look at the metrics that we have on the right, you can see that the investment was only 50 million, right? The total investment, the total loan that we got was 50 million. Our profit per year, it is around, like if you look right here, when the products that we are selling, they are bringing in $354 million per year. That means that we do have a great deal of money left behind. Even if I pay my taxes, if I pay my TPC, I still have around close to $200 million left around. And that is why it is possible for me to pay off my loan within 0.2 years. That means in 0.2 years, I'll be able to pay off all of my capital investments. All of my investors, they will be paid off. All of the bank loan, that will be paid off. And I can start putting all that profit into my own pocket. The reason it is very low right now is because, as you can see on the right, it's because we are making a great deal of money from sales. Sometimes I have worked on a project where the payback period was 8 years. And if it is 8 years, then it's not very acceptable, because that means that you're not going to be making that, you will not be able to pay off your investors in a good amount of time. Finally, the minimum selling price, that is the price that we need to be selling our product, which is biodiesel. That means that in order for us to create a profit, we need to sell biodiesel at a minimum price of $0.29 per kilo. If somehow there is a market crash, somehow there is all of a sudden too much biodiesel in the world and the prices plummet, they cannot go below $0.29 per kilo. If they do go below $0.29 per kilo, that means that we will not be able to make a profit. And that is what essentially the minimum selling price is. And if I just go back, apparently there we go. I can show it to you right here. The price of biodiesel that we have selected is actually $0.29 per kilo. So already there you can make an assessment and say that it would take a lot of uncertainty or a market crash to bring biodiesel down to 0.29. So in that way, you can always argue that our process is indeed very robust and profitable, because we are in a very, very safe zone in terms of the minimum selling price. Now, if you look at all of these metrics, if you take a general overview and a general assessment, we can conclude that our process, our biodiesel production, is indeed a very profitable process. It is very profitable. The reason being that the all metrics, they agree with each other, and our investment is, we are getting more and more compared to our investment. Our time value increases all the way up unto 1,264. We are going to be able to pay back our loan within 0.2 years, and the minimum selling price is way below our current selling price. So in that way, we can conclude that biodiesel production is profitable, and whoever wishes to do it, they're going to be making a great deal of money out of it. But the thing is that the calculations that we have done so far, they are all theoretical. They're all based on literature. They're based on sources. They're based on different relations that we have found from different areas. In reality, you have to be able to understand. You have to be able to assess. You have to understand as an engineer that these things can change. There is one thing doing the engineering legwork. that is not affected. That is only under the command of an engineer. You go in and you can change the variables as you like. The pressure, the temperature, they're not dependent on the outside world. But the techno-economic analysis is something that is directly linked up with forces that we can't control. This entire process is dependent on something that is out of our control. The international market, the political stability of your country, for example, when we saw the COVID crisis, for example, it came up, the prices, the market crashed. That is something that we cannot control. And therefore, we have to do something called a sensitivity analysis in order to understand how robust this entire process is. If there were to be any deviations within the prices of, let's say, raw materials, product, of our utilities, waste, and any other variables. Let's say, what if you wake up one day and your government decided to raise the tax from 30% to 50%? You can't just go and say that I don't feel like paying tax, because you have to pay tax. That is something that you have to keep into account. Likewise, right now we are buying waste cooking oil at $0.2 per kilo. But what if your supplier gets greedy and he finds out that you're making a great deal of money out of it, and he actually triples the price? Because that's how it works, right? If there is a very high demand, then the prices go up. And that is something that will happen with waste cooking oil if this thing is commercialized. And that's why you have to take that into account as well. So therefore, what you do is that you select an interval, you select the percentage deviation within each of these variables. So then you say, there are two ways of doing it. The first way is that you go from -100 to +100. So you select a value, the waste cooking oil, for example. Let's say the cost is 0.2. You decrease it all the way up until -100. That means that let's say the price decreased in value, decreased up until -100, or it increased by 100%. With different intervals, you could do 10%, you can do 555%. Anyhow, you go from -100 to +100. Then you can plot a scatter graph to show how it affects the economic metrics. Or you can do something where you select a predefined percentage, let's say 30%. Then you only do -30% and +30%. When you do those, then you plot something we call a tornado plot, where you have a line in the middle, and it will show you how it deviates on both sides. For the purpose of this slide, of this webinar, I have decided to go with the -100 and then +100, because the research paper that I shared with you before the webinar, that they have done tornado plots. So therefore, I thought that you could have a look there and see how it works, but they have not used the approach with the -100 and the +100. So therefore, I decided to go with that. And majority of the time, the changes that will come, they are in the raw materials, product price, utilities, taxes. And that's all. They are the only ones that are mostly uncertain when it comes to your economic analysis. So, like I said earlier, so you can do the -100 and then the +100. I'm sorry. And then once you do it, the thing is that it's not simply enough to just plot line. It is very important that you understand that what is the effect of each and every variable on these changes. So if you look at the payback period, the payback period is something that is directly related to our capital investment. So the payback period is going to be more affected by our investment value than it is going to be affected by our ongoing expenses. The reason being that the ability, the expenses only affect our ability to pay back our loan. But if the capital investment is increased a great deal, that means that we will have to pay a lot more money back, and hence the payback period would increase. Typically, the payback period is much more sensitive to capital investment and essentially equipment cost than it is to our other costs, like such as raw material cost or our product cost. The product cost, if it changes, it affects the ability for us to pay back the loan, right? And you can see right here, if I change my biodiesel price, which is this orange line right here, if the biodiesel price increases, if it increased by 100%, you can see I can pay back all of my loan within 0.1 years. So it literally decreased by almost 50%. If my biodiesel price increased by 40%, and actually you can't see it in this graph, but if we went down to 60%, it would take us 8 years to pay back the loan that we have taken, to cover the expense, the capital investment. So that means that our payback period is strongly dependent on our biodiesel price. If there is any change, if there is any decrease within the biodiesel price, that's going to affect our profitability negatively. And that is very important. That is something that we have now understood in terms of the payback period. And then we come on to the return on investment. The return on investment, like I said earlier, it is the amount of profit, fraction of the profit divided for the annual profit divided by our initial investment. Now, likewise, if there is any change in our biodiesel price, it affects the ROI strongly. You can see there is a very strong change in our value compared to our waste cooking oil and our utilities. You can see the utilities, they have no influence on our ROI. Likewise, the waste cooking oil has a slightly medium influence. Why? Because if the waste cooking oil price goes up, that means that we need to pay, our profit is going down, right? The less the profit, the less of the fraction, and therefore the ROI is going to decrease. But since the waste cooking oil is not very expensive to begin with, therefore, even if we increase it by 100%, then it is not very much affected, and we are still very much in the profit zone, which you can see right here. Even if it increases by 100%, our ROI will still be 200%, which still that means that we are still profitable. On the other hand, if our biodiesel price decreased by 70%, that means that we are no longer profitable. And I wouldn't even go up to the 70%. I would say if we are at around 60%, already there, we are hitting that around 50% mark. And already from that area, we can say that we will no longer be profitable. Likewise, and because you have to remember that when we are looking at the curve of biodiesel, if you are at this stage right here, that means that you don't have that much place for other changes. So if your ROI is only 50% to begin with, and if at that level you have changes within waste cooking oil or utility cost, then you would drop down to zero fairly, very quickly. Therefore, you could always argue that around 50 to 60%, that is the limit that we can set. If the biodiesel price decreases by more than 50%, we are no longer profitable in terms of our return on investment, which you can see even now. Return on investment and the payback period, there is a strong agreement between the two, right? From this, we also found out that if we go below 50%, the payback period is more than 8 years. That means that 50% is a limit in terms of PPE. Likewise, 50% is the limit in terms of ROI. That means the main variable that the pillar of our profitability is the biodiesel price. Likewise, the net present value, this is the money, the time value. The more money you make, the more value you have. So in that way, in that regard, it is of course common sense that the more expensive biodiesel is, the more money we make. The less expensive it is, the less money we make. So now, finally, so once you do all the analysis, luckily in this case, it was profitable. We made a great deal of money, which was amazing. many times you don't make that much money. Instead of waste cooking oil, let's say if I had used soybean oil. Soybean oil has a very strong market, it's a very strong demand, and it is a very scarce material as well. Therefore, it actually costs around, I believe it costs around $0.8 per kilo. If I had used $0.8 per kilo as a price, we wouldn't be profitable at all. Because if you look right here, right now, waste cooking oil costs only 75 million, and it only costed $0.2 per kilo. If we had used a more expensive oil, it would have been at the same level as biodiesel. And that means our profits would not be very high. Therefore, the first step is to understand if you can use a cheaper material to start with, or if you can, you should do it. Many times it's not that simple. You can't just take a random raw material. Of course, it has to fit with your overall process, but that is how you do it. Finally, the utilities, they tend to be a bottleneck. You could do heat integration instead of using so many heat exchangers and to use steam and cooling water. You can do heat integration to if you have a process stream that is very hot and a process stream that is very cold. You can connect them if possible, and you can do the heat exchange there. You could save a fortune on utility cost. Finally, you have waste treatment. If you have a waste stream that you feel that you can purify and then sell it off as an actual product, you should do that, because instead of having to pay 2 million, you might end up earning 2 million. And every single penny matters when you're doing this techno-economic analysis. The biggest example is water disposal. If you have water, like for example, I designed a process once where I had a fermentation reactor, and we were using water to dilute the process. After that, the same water then goes out. It was not being used anywhere. Instead, all that water then had to be removed from the process. 90% of the waste treatment cost was in the water disposal cost. And that's, I mean, there's no point of literally giving away all that water. Instead, what you can do is you can either create a you can design a water treatment plant right beside your process and clean the water and then reuse it back into the process. It may seem that it's going to cost you a lot more, and it will, in terms of your equipment cost, in terms of your utility cost, but in the long run, what you're doing is you're saving a lot of money. Because if you have to buy water every time, then you're no longer dependent on the market deviation. The sensitivity is okay. It doesn't matter because you only have to buy the water once. Then you can recycle the water, and it helps in the sustainability area. But these optimization techniques only work if you have money in hand. Like, for example, I said the water treatment, like, let's say it ends up costing you 5 million extra, but you only have 2 million in pocket to pay for it. Therefore, you always have to keep in mind that these things are interrelated. And something that I was told when I was doing it, that half of the things are common sense. As an engineer, you need to use your common sense and to make sure if these things work or they don't work. And I believe that is all I had to say about techno-economic analysis and the biodiesel production. So if you guys have any questions, you can feel free to raise them in the chat, or you can unmute yourself and ask.
Hi there.
Yes, hello.
Thanks. Yes, hi. My name is Akil. I'm dialing in from Cape Town in South Africa.
Mm-hmm.
I'm a master's student at the moment in chemical engineering at the University of Cape Town.
Mm-hmm.
Thank you very much for the presentation, Chemical Engineering Life, and thank you very much, Humzaa, for the
Thank
interesting presentation. My research project is actually on a new process developed by the University of Cape Town, where I'm conducting a Techno-Economic Analysis on this new process in collaboration with a commercial partner, with a cosmetics raw material producer. And therefore, going further than just kind of the theoretical techno-economic analysis, a lot of my work, or a lot of the focus of my study, is in fact to get actual equipment costs and actual cost estimations for many of the inputs to a model like this. And I'm glad that you also mentioned, under the uncertainty analysis, the Monte Carlo simulation, because a big part of my project is in fact conducting a Monte Carlo simulation. And I'm doing it in Python, just because of the programming abilities of Python. But I mean, a lot of my difficulty is just finding relevant factors, both from literature and from suppliers and commercial partners, to as reliable inputs into my process. Maybe my question then, just to the broader audience, is, are there very reliable and well established and well understood resources, handbooks for not only for literature, because a lot of the literature I've gone through is laboratory based studies, using utilizing the performance of laboratory equipment such as centrifuges, etc. What is out there in terms of the more industrial, or information on industrial equipment performance? So for centrifuges, for aqueous two-phase, a big part of my project is understanding the aqueous two-phase system, which liquid layers. So yeah, if anyone, or if yourself and anyone has come across such resources, where could they be found?
Yep, I mean that is a very good question, and let me begin by saying it's not easy. It's very difficult to find these sources and these factors, especially for equipment that you mentioned. Like it might be very easy to find it for flash tanks, but when it comes to some less used equipment, it tends to get very difficult. And the way to do it is that like what I did was, when I was doing my thesis back in the day, when doing my Techno-Economic Analysis, I used this I have forgotten the name of the organization that have done the paper, but I can share that with you later on on email, because they have validated and verified an industrial example and all the factors that they have used. So I would suggest that you can use that, and I believe they have given examples of centrifuges, flash tanks, and all of it. And I believe I'll find it and I can share with you right after, because the name of them is not coming in my head right now. But typically, I use those. And like I also said earlier, that it's always a good idea to use validated papers and verified organizations to take these values from, because there are multiple research papers that you can use, but many of them are theoretical, and there are a few papers out there that are based on industrial examples. And the one that I'm referring to right now is actually based on an industrial example that has been implemented, and from that they found the values. You could also, so that's regarding the equipment cost and the factors. Secondly, you could also, what you could do is, like I said, so there's this book, this Plant Economics and Design for Chemical Engineers. It is a very good book. They have defined the methodology, and they have defined the constraints, the brackets for different factors, especially when it comes down to, like, for example, how to calculate the capital investment, how to calculate the TPC. So I would strongly suggest you use that as well. But
is that by any chance the textbook? Sorry, is that by any chance the textbook by Turton?
No, it is by Peter and Timmerhouse, I think.
Peter and Timmerhouse. Okay, I'll take a look at that.
Perfect. If it is, I'll share the information of all the papers, the video right after the webinar, and actually with everyone that is in attendance, so you all can have a look at that on the material. But but you just have to look out for all these equipment. Like, for example, when you working with utility cost, for example, I I designed this plant in the US, so then I used their this what they call it, the EPA, I think, not EPA, like their national electricity organization. I don't know what the name is, but I went to their website and I used theirs. So if you're doing it in Cape Town, for example, then instead of using literature to take the values, it's always a good idea to just take directly values from the actual company, countries, your, like, what do you call it, the people that are providing electricity and so on. So that's one way to go about it. Yep.
Thanks for that answer, and it will be great to receive those resources.
Of course, I will.
Coincidentally, I'm also busy with a chemical engineering consulting project for a company in Kenya that wants to turn an alternative oil source into biodiesel. So it's quite interesting seeing the. I know of a few other companies that use waste cooking oil, and as you presented, the conclusion, I guess, based on engineering judgment and common sense, is that using waste cooking oil will be very profitable because you're paying very little for your raw material, and methanol isn't expensive either. Yeah, but so it's quite interesting comparing the Techno-Economic study that I've done on this alternative oil and viewing that against waste cooking oil, and even the literature that I've gone through. Many reports say that biodiesel from the traditional oil sources like soybean or anything else is that the profitability is extremely sensitive, which is why I think not many companies are currently into it. I believe there was a boom in the early 2000s where everyone wanted to kind of produce biodiesel, but the economics were just too sensitive for any investor to really buy in long term.
Exactly.
But yeah, these alternative waste or these alternative oil feedstock streams are becoming very popular just because of that economics, because of the difference between the biodiesel cost and that raw material cost, which I found was quite important.
Exactly.
So yeah, thank you for the very interesting presentation.
No, well, thank you. I fully agree, because the thing with soybean oil is that the soybean oil itself is in a very high demand as a raw material. So you can use soybean to produce so many other products. And like I said, so like already at this stage, you can look at it. You can say that biodiesel, it sells at a price of $0.9 per kilo. Soybean itself costs around $0.8 per kilo. So the only profit you're going to be making is 0.1, and that is a limitation when you use these oils. But luckily, the waste cooking oil, and I personally believe that is a very great way of producing biodiesel, because I mean it's a waste stream. You're not really using it for anything else. You don't have any other competitors for waste cooking oil, and that is of course the main reason why it's so cheap. But in reality, maybe in coming years, it will also become more and more expensive as we get. But hopefully, so will biodiesel as the demand goes up. So you're very right. That's
Just I actually know of one company that I was once in discussions with. It's a company called Neutral Fuels, based in Dubai, in fact. And their whole business model is based on using waste cooking oil to convert to biodiesel, and then selling back that biodiesel to the commercial partners that they get the waste cooking oil from. So they're very targeted in terms of their marketing and their commercial relationships with a lot of major restaurant chains. And some, I think, logistics, companies, which are obviously very interested in being able to reduce their carbon footprint while achieving some cost benefit from using an alternatively produced fuel.
Exactly.
So that would be quite interesting to look out for yourself as well, if you.
Exactly. Yep. Thank you for that. Interesting. That's quite interesting. And like you said yourself, it is quite profitable. So a lot more and more people are going towards it. It's a good thing, I think it's a good thing that we're moving away from petroleum towards, like for example, waste cooking oil. I believe only in the U.S. they produce like millions of barrels of waste cooking oil, and it is a waste product that we cannot get rid of. So if companies like that are investing in reusing that, then it's great for the environment itself. So it's great that it can work out for everyone.
Yeah.
And what was the name of the company that you mentioned? Sorry.
Neutral Fuels.
Neutral Fuels. Okay, great. Yeah. I remember to check them out. So thank you.
Yeah, definitely.
Does anyone else have any questions? Okay.
Okay. Hi, I'm Emmanuel.
Hello.
I'm Emmanuel Anthony Emmanuel. I'm a master's student in Biorefinery, an Erasmus joint master's program. Thank you once more for the very enlightening session. It was really wow. I would not know how to describe it. But then one area of concern for me, it's that I feel really has a huge impact on the economic assessment of bioprocesses or future bioprocesses, of course, is supply logistics. The supply logistic chain. You just said something like there's a huge amount of biodiesel produced worldwide. I mean, waste cooking oil produced worldwide. Yes, it's a good option for biodiesel production, but the supply logistics is not, the supply chain is not really effective. It's not, we don't have existing supply chains. And how does this inability, this variability in supply exactly affect this economic analysis? I don't know if there's a huge impact of this non-established supply chain in the to the economic viability of a project.
Yep, that is actually a very good question. That is an excellent question. And the problem with waste cooking oil is that it is not a commercial product, right? So we don't have companies that are like gathering waste cooking oil in tanks, and then you can just give them a call and have them brought that to us, right? If you read the research paper that I wrote, the price $0.2 per kilo, that is actually the price that was calculated based on the transportation cost. So what I did was that when I was doing the calculations, is that we calculated that on typically how much does it cost to transport this oil from one place to another, and then I believe we take a reasonable transportation, what do you call it, the distance, and then based on that, then we calculated the waste cooking oil price that we will be paying for it to be brought to us in terms of supply chain and from the supplier. And that is actually one of the reasons why it was so cheap to use it using the source that I picked. If you dig deeper into the supply chain, and if you have people that are gathering waste cooking oil in one place, they have these, let's say, huge tanks, and then they give you the waste cooking oil, automatically it's going to be more expensive. That is the limitation with it. And you said it very correctly that the supply chain of waste cooking oil is difficult because it's not very easy to assemble. You could go to different restaurants and you can ask them to give them to you, but it is very difficult. And that is a huge limitation in the biodiesel production, because it's one thing saying that you can use biodiesel and you can have it transported to you to produce biodiesel, but having to gather that amount of waste cooking oil is a challenge in itself. And I believe that is one of the main reasons why waste cooking oil has not really been used yet commercially to produce biodiesel. And just like you mentioned earlier that there are different companies now that are moving towards it, but in reality, in a general scale of things, the reason waste cooking oil has not really been commercialized or not used, I believe in 2019, around the globe, only 17% of the global production of biodiesel is by waste cooking oil. And even less than that, and that 17% was still an exaggeration. And the main limitation of using waste cooking oil is actually the supply chain. And that strongly affects the economic analysis, because if you say that you want to produce biodiesel and you are going to go out there and gather waste cooking oil from all these restaurants that are in your area, that is one thing. But let's say you're living in I don't know, in New York, and you want waste cooking oil brought to you from Texas, then you need to take into account that the transportation cost, all that stuff, that's going to increase the price of waste cooking oil. Likewise, if you reach out to a company that are gathering waste cooking oil and they are selling that to you, then it's even going to be even more expensive. And so you're very right. So therefore, that is a strong question mark on the techno-economic analysis about how you're going to gather waste cooking oil. And if you do it through how you do it with the other ways, then it's going to be more expensive. If you do it yourself in terms of transporting it to or gathering it from different areas, then it's still going to remain slightly cheaper than if you were buying it from a middle person. I hope that answers your question. If I didn't go away from what you asked.
Yeah, you did answer it quite well. But then I was probably thinking in my head, because I'm quite too devoted to sustainability. if we kind of approach it from the triple bottom line of sustainability, talking about before we look at the economic aspect, maybe we could focus on the social aspect. Because when Andrew spoke the last time, he said there were some companies who had the social relationship with restaurants and like sources where they get this stuff. It could really help a lot in gathering this raw material, because nobody, for now, it's looking like a waste. But when it becomes a big deal, everybody will begin to hoard it, and the price increases. And when the price increases, it affects the overall sustainability of our project. So I think the major aspect to look at is the social aspect, because most or a larger quantity of this oil comes from restaurants and homes. And if there's no established relationship between the suppliers and we or the builders of a biorefinery who needs this waste cooking oil, I'm not sure there will be this constant supply. And that way our analysis would always be false.
Exactly. And that is very true, because just like how earlier was mentioned, back in the early days, when soybean oil became this talk of town, it actually used to be very cheap as well. But then once people started to realize that it can be used for so many things, the price simply skyrocketed. And that is one of the reasons why we do this sensitivity analysis. And like I showed you earlier, like in this case, we only went up until 100%, right? But in reality, it could go a lot higher than that, because just like you correctly mentioned yourself, once people start to realize that the waste cooking oil can be used to produce biodiesel, which itself is a very expensive product, and you can create an ROI of 300% per year, people are automatically start going to hoarding it, and restaurants and houses, they are going to start selling it to us at an additional price. Even though nowadays people are simply just throwing it out, but in the coming time, they will start holding it and start selling it at a much higher price, which will limit the profitability of biodiesel production. And that essentially is the bottleneck right now when it comes to bioprocesses compared to petroleum fuels, because the reason petroleum fuel is so lucrative, so expensive, much more one could say profitable, is because they don't have these loopholes that biodiesel currently have, especially because when you're using oils. Because right now, to be honest, when you think of soybean oil itself, it's not that much of an economical problem, but there also tends to be an ethical problem. Like, does it make sense that we start using soybean oil instead of for feeding different people, we start using it for biodiesel? That's also a question mark. That's also a problem why you can't use it for production, and all this expensive. The waste cooking oil, even though it's a waste, it will get more expensive. I have found sources where some companies in England, I believe, even in the US right now, they are selling waste cooking oil at prices as high as $0.6 per kilo. So it is being commercialized, and the higher the price it goes, the less profitable the biodiesel production will be, and it is sadly a limitation. But then, as an engineer, then your job is indeed to find ways that you can optimize the economics of the process, because if the raw materials are going up, then you have to find different ways in which you will have to increase your profits from your production. And that is something that you have to look into, something we call a process integration, or something, you can go down and you can, for example, right now, the research paper that I shared with you before, glycerol is a very low-end product, for example. You can use glycerol to produce succinic acid. Glycerol, it sells at around $0.8 per kilo. And that 0.8 is actually very high because the market of glycerol has plummeted. So it even sells as low as $0.3 per kilo. But if you use glycerol to produce succinic acid, then you have two processes. Then you're selling biodiesel and you're selling succinic acid. And succinic acid sells at around $1.2 per kilo. So, so in that way, you can increase the profitability of your process to make it more competitive to petroleum fuel. I hope that answered your question as well.
Yeah, very well. Thank you very much.
Thank you. Then I can see someone asked a question, Mansab. It is because in the paper that I shared, the paper, it is an example of process integration. So there are 3 different processes within that paper. So you actually have, so the thing that I just mentioned right now, so we have biodiesel, but because biodiesel cannot be as profitable compared to petroleum fuel, and just like we talked about that waste cooking oil, it will go up in the coming days. So therefore, the approach that we took was that we integrated biodiesel with succinic acid, succinic acid production. By doing so, we increased the portfolio in a way. In the same time, the methanol that we are using as a raw material, instead of buying methanol, we actually produced methanol in-house using methane, CO2, and water. And that's what you're looking at as the raw material. So you have, in the paper, there are 3 different processes. The first process, that is the methanol production. The methanol from the first process was then used to produce biodiesel, and then biodiesel, then we got biodiesel, and for biodiesel, we are only using waste cooking oil and methanol. And then the byproduct stream from biodiesel was then used to produce succinic acid. I hope that answered your question. And I'm sorry I didn't make it clear in the information that was sent out, but for this webinar, we decided only to look at the biodiesel production and not the other 2 processes that were discussed in the paper that was shared with you all. And yes, of course, I'll share my email with you. So if you guys have any questions, you all can feel free to reach out anytime to ask about the Techno-Economic Analysis. And regarding the simulation, I'm afraid I cannot share the simulation with anyone because they are protected by the by some confidentiality agreement. So I'm afraid I cannot share the process simulation file. But if you have any question, I'll be more than happy to help you and answer any question that you guys may have in terms of the simulation. Does anyone else have any other questions? Great. Then I think we are also a bit over time now. So thank you to everyone that joined in today, and thank you for listening to me speak. And like I said, I will share the literature that I have and also the different other textbooks that I have been using for Techno-Economic with you all, so you all can get a chance to also use them in your future projects if you wish. And if you guys have any questions or about any of it, feel free to simply, I'll also share my email with all of you, and you all can simply reach out anytime you like.
Great.
And I was told.
Thank you so much, Humzaa.
Thank you.
Thank you everybody for joining us today, and thank you, Humzaa, for making us smarter on the techno-economic topic. I definitely feel like I have a bit more knowledge here now. And thank you everyone for being such a great audience. To be a part of such webinars in the future, make sure to become a member on our website, and this webinar will be uploaded on YouTube, so you can rewatch it anytime if you feel the need to revisit the topic. And as Humzaa mentioned, he will be providing you with his email and contact details, so I hope you will use those to your benefit. And of course, on YouTube and our website, please don't forget to like, subscribe, share, comment, all of that. That helps us a lot in keeping this a free environment and keeping you guys educated on the different chemical topics. So with that, I would like to thank you all, ladies and gentlemen. You have all been a lovely audience. Have a lovely Sunday.
Thank
Bye.
you. Thank you, everyone. Thank you.
Thank
Bye-bye.
you very much.